Recording. Couple of things. First of all, 9 of you have submitted your homework. Congratulations to the 9 of you who have submitted your homework. Yay, nicely done. Remember that is due by noon. So homework today due by noon. I got a couple of questions via email that I answered this morning. So hopefully those are all set and good to go. Personal grading schemes are due Monday, so don't forget to take a look at that personal grading scheme. If you need to handwrite it on a piece of paper and turn it in, that is absolutely fine. Whatever needs to happen is not a big deal. So if you need to handwrite it on a piece of paper, take a picture, whatever you need. If you want to type it out and email it as a Word doc, that's fine too. But Monday at noon, so I can get those personal grading schemes updated, please and thank you. My goal for grading homework is I'm going to head into WLC because I don't have a printer at home, and traveling for is considered essential. So I'm going to print your homework, and then I will either take pictures of it or scan it in and get it back to you. But I am so tired of looking at a computer screen that I don't want to grade homework on a computer screen. I don't know how computer science majors do it. Really, you guys, I don't know how you do this. I am so tired of looking at a computer screen.
Dr. Schultz even prints out the computer science assignments to grade, so.
Okay, that makes me feel a little better. So yes. Those are my 2 reminders. Anything else for procedural questions, etc., that people have at this point in time? Anything? Okay. So then here is where we are at. Today is our last day on digital signatures. So we've talked about a couple of digital signature schemes so far, right? We did RSA and we did Algamahl. Those are the ones that we did last time and before break. And remember that both of those are based on encryption schemes, right? They're basically the RSA encryption scheme, and then the RSA digital signature scheme is encryption in reverse, basically what happens. Sort of, kind of the same with Algamahl, not exactly, but there's still an Algamahl encryption scheme, and then there's a signature signature process associated with it also. Today we're going to do one more, and there are tons and tons of them out there. These are just the ones that I happen to pick that I want to cover. Today we're going to do one more that is not based on an encryption scheme. So this is just a standalone digital signature scheme. That's what we're going to talk about today. Monday and Wednesday next week we're going to do primality testing. And then next week, Friday is review. And then the following Monday, April 6th, is going to be the next test. So that's our dates of stuff. Please tell me that that's what I put. I'm losing my mind. Please tell me that that's what I put on the class website. Ashley is nodding me. Okay, good. All right, so that's the plan running up until the next test. So any questions on that before we get going with the digital signature scheme? One more for today. Anybody, anything? Okay, let me share my screen and get the PowerPoint up here. And we'll make that full screen. And again, remember, now I can't see you. So if you have a question, please feel free to ask, but you got to raise your hand virtually because I can't see all of you. Maybe I can. Yeah, I think I can. We can do it this way because I can get my stuff in front of me. Okay, I can see all of you. Okay, digital signatures. So remember, just a quick review. These are posted on Moodle also, so if you want to take notes, you can. Alice signs the message. Remember this, we've done this before. Bob needs to be able to verify that Alice actually signed the message. So that means there's 2 steps, a signing process and a verification process. And remember also that signature schemes are separate from encryption schemes. So we are going to assume that this message gets encrypted some other way. Not sure how, don't really care at this point in time, some other way for encrypting this message. And then we are just going to work on the signing and the verifying. This should all be totally and completely reviewed. Give me a thumbs up that this is all totally and completely reviewed. Cool. All right. Here's the one we're talking about today. It's called the Digital Signature Algorithm, DSA. And it was proposed in August. This is the history that you don't have to know, so don't bother taking notes on this, but this is a real live math class, and so I like talking about the history. It was proposed in August of 1991 by the National Institute of Standards and Technology, NIST. And I'm guessing none of you have heard of NIST before, not many, probably not unless you've come across it in research for your paper. NIST is a prelude to something that you probably have heard about, which is the National Security Agency, NSA. So NIST kind of turned into the NSA, sort of kind of they're related. Okay, so it was proposed in August of 1991. It was formally adopted in 1993. It was revised in 2000, 2009, and 2013. It may have been revised again since that, but normally I have a note for myself to go and check what the latest revision date is, and things are a little crazy with online learning right now, so I forgot to check what the latest revision date is. So there may be another one besides 2013, sorry. It was, and again, normally I make a note to check myself, it was used by the US government for generating signatures. I'm not sure if it still is. I'll try to remember to do some looking. Usually used by non-military government agencies and government contractors. And it's what's known as a FIPS, which is a Federal Information Processing Standard. So all of the information on this slide was good 2 years ago when I taught this class. I am not sure if it is still used by the US government now or not. My apologies, I should check on that. But like I said, things are kind of falling by the wayside here. Okay, here's the basic overview before we get into the nitty-gritty details and parameters. So what DSA is designed to do is optimize signatures at the expense of verification. That's what's supposed to be happening with this one. We are trying to optimize signatures at the expense of verification. So what that means is that the process of signing a message is really fast, really easy, but verifying a message is slow and harder. And again, I am using easy and hard in terms of speed and computer science stuff. So fast means easy, slow means hard. It's not necessarily a hard process. There's not necessarily hard math involved. It's just slower. It's just a slower process that we are going through, and it takes longer to verify than to sign. This led to some criticism of the digital signature algorithm, because usually what happens is you sign a message once and then you verify it a bunch of times, because you can imagine someone is signing a message and then it's like a memo or something like that. They're sending it out to a whole bunch of different people. And so all of those different people are going to be verifying the message. So it seems like this process is reversed from what it should be. It seems like signing a message should be slow and verifying it should be fast, because that's usually the way that the process goes in terms of what needs to be done more often. So it might potentially make more sense to make signing hard and verification easy. But again, this is the government. They came up with it. They said, we like it. We're not changing it. We're using it. So this is what we have at this point in time. All right, so that's the basics of DSA. We can get into the specifics, the parameters, and the protocol in just a second, but everybody's good so far? Basics of DSA, give me a thumbs up, nod, yes, good, okay, cool. All right, here's the parameters. We'll talk about these first, and then we will talk about the process or the protocol. So we've got a couple of things. Excuse me. First of all, P is going to be a prime, and I have usually 512 bits. It doesn't have to be, but that's the way that this protocol was initially written, that P was a 512-bit prime. Q is going to be another prime, but Q needs to have a special restriction also. Q needs to divide P minus 1. And I want you to keep an eye on where this is going to come as we get into the protocol. So remember, this Q has to divide P minus 1, and we're gonna look for where that requirement is necessary as we're going through. All right, G is an element of ZP star. So that two things are true, but let's remember ZP star first. So remember, ZP star is everything less than P, positive integers, and relatively prime to P. Less than P, relatively prime to P. And because P is a prime, you have 1 through P minus 1, because everything less than P is relatively prime to P. Okay, so that's just a fancy way of saying that G is between 1 and P minus 1. But a couple other things have to happen. So first of all, G raised to the Q mod P needs to be equal to 1. That's our first requirement. G raised to the Q mod P has to be 1, but G itself can't be 1 mod P. And the second one is kind of redundant. Actually, the second one is very redundant because G is supposed to be an element of ZP star. I've never thought about that before. Okay, the second one is redundant and we don't really need it, right? Because if G is less than P, then G can't be 1 mod P unless G is equal to 1. So we're just saying G is not equal to 1 here. We also have this A. A is going to be an integer. All right, and then we're going to create a value of B, and we've seen this before in Algomal. We created B this way also. B is going to be G raised to the A mod P. That's it for the parameters. That's a lot of parameters, but that's what we've got up to this point. So we've got P, we've got Q, we've got G, we've got A, and then we generate B. So we basically start with 4 parameters, and then we generate a 5th one. Okay, all good? There are global values. So these are a public key, are they? Yes, these are a public key and these are used by everybody in the system. It's kind of like when you were doing RSA and N or P and Q is used by everybody in the system, right? These are the values that are used by everybody in the system. The public key is equal to B. So this is some specific person's public key. And then that specific person's private key is A. So if you're looking to use DSA, everybody uses the same values of P, Q, and G, and then you generate your own values of A and B. A is what you keep secret, B is what you make public, okay? What's the problem? That makes A hard to find given everything else on this list. You should be very familiar with this problem at this point in time. Why is A hard to find given everything else on this list? Somebody give me an answer. What do you got? I can see you all, so you can just unmute yourself if you want, or you can raise your hand and type it in. What's my problem? Why is A hard to find given everything else on this list? What's my problem? What do you got?
Discrete log problem.
Thank you, John. That is, in fact, the discrete log problem. Yes. So once again, we have the discrete log problem that makes A hard to find. All right, we're good with the parameters. Ready to move on to the protocol? Everybody's good? Yes. Okay. Here's the protocol. So, oh, I lied to you. I'm sorry. So how do you, there are restrictions on P and Q, right? So how do you usually generate these things? This one is a little bit optional. You don't have to do this for DSA, but it's going to help you to find P and Q that actually work. So what we usually do is instead of starting with P, we're going to pick Q instead. So we're going to start with a random prime number Q, and then we are going to let P be 2 times J times Q minus 1 for some random value of J. 2 times J times Q minus 1 for some random value of J. And if we get something that isn't prime, we'll try again. So this is the way that we usually generate P from Q. And I'm going to go back a slide in just a second and tell you why we want to do it this way. So 2 times J times Q plus 1. And the reason for this is because we needed Q to divide P minus 1. Second bullet point on this slide here. Q need to divide P minus 1. Usually I would walk over to the chalkboard and write on it at this point in time, but this is a little harder to do. So in this case, if you look at P minus 1, Q is going to be a factor of that, right? Rearrange that equation a little bit in the second bullet, and Q is a factor of P minus 1. So this gives me a relationship between P and Q. The way that we generate G, this is the way that we usually generate G. We want to pick some random value of H, and we're going to let G equal this. H raised to the P minus 1 divided by Q mod P. This looks messy, but we'll tell you why we're going to do this in just a second. G is equal to H raised to the P minus 1 divided by Q mod P. And remember, we can't have G equals 1. So if G equals 1, we'll just try a different value of H. Okay, couple of things to talk about here. Two things. First of all, I am dividing in the exponent, p minus 1 divided by q. I have to be really, really careful about dividing in the exponent. What fact did I have on the previous slide that lets me divide in the exponent? What was my good thing that is happening that lets me divide in the exponent? I told you I was going to come back to this and ask. What do I have that lets me divide in the exponent and not worry about getting a fraction? Somebody help me out. Unmute yourself.
P minus 1 is divisible by q.
Absolutely. Thank you, Seth. P minus 1 is divisible by q. So since P minus 1 is divisible by q, I know I'm going to get a non-fraction in the exponent there. Okay, the second thing that I needed is 1, 2, 3, fourth line. G raised to the q has to be 1 mod p, right? G raised to the q has to be 1 mod p. So let's go ahead and look and make sure that happens. So G raised to the q, I put this all on one line. If I look at what my G is, that is h to the p minus 1 divided by q, and then all of that is raised to the q. You multiply exponents, so you have, can you see my cursor on my slides at this point in time, or no? You can. Okay.
Yes.
So you have, good. You have a q in the denominator and you have a q in the numerator. Those are going to cancel when you multiply them through. And so you get h to the p minus 1. There's a mod in here. I'm just kind of putting it all the way out at the end. Why is that equal to 1 mod p? What's the name of the result? What's the name of the theorem? We haven't talked about it for a while, but it's a super important one that comes up lots and lots. The name of the result, the name of the theorem that gives me h to the p minus 1 equal to 1 mod p. What's that theorem? What's that result? People are now thinking and trying to remember. Remember that one? I'm going to take a drink of water while you're thinking. Anybody got it?
Is that Fermat's little theorem?
Yes, thank you, Sarah, John. That is Fermat's little theorem. It could also be Euler's theorem if you wanted to, because Euler's theorem is a more general version of Fermat's little theorem. But that's Fermat's little theorem. All right, so practically speaking, this is how we usually come up with P and G based on Q, so that we can make sure that the values that we have actually work with the requirements from the previous slide. All right, give me a thumbs up that we're good with all of these values, and I can talk about the protocol and how to sign messages. All good? Excellent. Okay. So here's how we want to do it. We're going to sign a message M. Here's our process, and this is horribly complicated. It's not so bad, but there's a lot of steps. I think today I am going to demonstrate this on Perry just because I want to make sure that we see how it actually works. But we want to pick a random K between 1 and Q. And then our signature is going to be an ordered pair again, Y comma Z. So our signature is once again an ordered pair, like in El Gamal. We had ordered pair signatures there. Here's how I generate Y and Z. So Y, there's 2 mods going on here. Y is G to the K mod P, and then you mod that by Q. So Y is G to the K mod P, and then you mod that by Q. And Z is M plus A times Y times K inverse mod Q. And if you happen to get 0 for Z, then you're going to pick a different value of K. So that's our only kind of check at this point in time. If you happen to get 0 for Z, you're going to pick a different value of K. All right, let's talk through and make sure that Alice has the information needed to generate a signature, but that nobody else does, that somebody can't falsify her signature. So G is a global value. Alice knows G, no problem. K is a random value that she picked, all good. P is a global value. Q is a global value, so we're good to go there. M is the message. Obviously, Alice knows that. A is Alice's private key, right? Remember back a couple of slides, that was the private key. So that is the secret piece of information, and therefore nobody can generate a message. Y we just did, K inverse, again, she picked a random value of K. And K inverse mod Q is going to exist because Q is a prime, so everything is relatively prime to Q. All right, I want to take a minute. I want to go to Perry, and I want to actually practice generating a message, and then we're going to come back to how we verify this. So any questions at this point in time before we go through and attempt to generate a message? Anybody, anything? Okay, let's get out of the PowerPoints here and look at Perry then. So, oops, that was not what I wanted to do because I can't see all of it. Well, maybe that'll work. Okay, we need to do a power mod first. You can see my Perry screen now, right? Yes, yes, okay. So power mod quick. Oops. Okay, all right, so tell me places that I need to start. I'm going to generate my global values, and then I am going to sign a message. So somebody give me a place that I need to start if I'm trying to generate my global values. What do you got? Somebody give me something. Go. Unmute yourself or do it in the chat. I can see the chat also if you want to do it that way. However you want to do it. Sorry, I'm going to close on the email.
Choose a random prime Q.
Okay, so Q is going to be, we'll do next prime after that. Okay, and then just as a double check, is prime Q to make sure that's a 1, that's a yes. Great. Okay, what else do I need to do to generate global values? Next step.
Choose a random value J.
Choose a random value J. So J equals, I don't know, we're just smashing a bunch of numbers here. There's my J. What do I need to do next? Next step?
You need to see if Q times J plus 1, or no, 2 times J times Q plus 1 is equal to a prime number.
Okay, so P is going to be 2 times J times Q plus 1. And then we'll do is prime P. No, fail. Okay, so J is going to be, we'll try J again. And then P, that. And then we'll do an is prime P. No. Okay. Ugh. Okay, so sometimes it takes a couple of tries. Ah. Okay. Maybe it'll work at some point in time. Oh, fudge. Okay, you can talk amongst yourselves while I'm attempting to make this work. Oh, good golly.
Is 0 true?
No, 0 is false.
Okay.
Badly. Oops. We might stop demonstrating this in just a minute, but we'll see if I can get a prime that actually works. Okay, 3 more tries and then I quit. Ha! Okay, there we go. Small values of excitement here. All right, next up, please. We have a P that is prime. What do I want to do next? Next step, somebody next step. Sorry, say it again.
Pick a random H.
All right, so H is going to be, and we're just putting keys on the keyboard, and then I need to compute.
G equals H to the P minus 1 divided.
Yep, so I'm going to do H raised to the P minus 1 divided by Q, and we want to do that mod P. And G is not equal to 1, so that's great. Let's do a double check and do a power mod of G raised to the Q mod P and make sure we get 1, which we do. That is good. Okay, so there's my global values. What are the other parameters that I am going to need in order to sign a message using DSA? Other parameters, what else you got? 2 more things. Oh, come on, people. Here we go. 2 more things. Back to the previous slide. I need
You need a K.
I will need a K in just a second, but before I can do that, I need private keys and public keys. So I need, I think somebody
A and B.
A and B. Yep, I do need A and B. So A is going to be, I don't know, 54, and B is power mod of G raised to the A mod P. Okay, so I've got all my values. Now I need a message. So we'll do my message, and I also need a random value of K. So there's my random value of K. All right, I need to generate Y, and I need to generate Z. So first of all, we need for Y a power mod, G raised to the K mod P. And then Y is gonna be, we'll turn this into a number, mod previous line, that's %42, and I want to mod that by Q. Oh, I'm missing a parentheses. Okay, so there's my Y value, 717, etc. And then I need my Z value also. So M plus A times Y times, oh, we should do K inverse first, sorry. K inverse 1 over K mod Q. And then I need M plus A times Y times K inverse. We need to do that. So Z is going to be that answer, %45 and Q. Okay, so I've got my Y and I've got my Z, 2 halves of my signature, Y and Z. All good? Everybody good? Everybody clear up to this point in time? You will be able to go back on the recording if you want to and see the Perry log. Daniel, question.
How can you do K inverse equals 1 over K mod Q? Or is that just like defined?
That's the Perry code. That's, yeah,
Okay,
that's your process in Perry.
That's not actually like, yeah.
No, that's not actually how you do it. That's just the command.
I'm like, okay.
Yes.
Yeah.
Okay, anything else for other questions?
Can you explain why you're using lift in those like 2 situations?
Yes, yep. So if I do mod, then the answer comes back as a mod number as opposed to an actual integer. And I want to make it an actual integer because I can't multiply mod numbers and actual integers. So lift will turn something that's a mod back into an integer and basically takes it as Perry doesn't like things that are in ZP star multiplied by things that are in the integers. And so lift takes things out of ZP star and basically just puts them back into the integers. That's what lift does. Does that make sense, Rachel?
Yeah, that helps. That makes sense.
Okay, anything else? Other questions on this? Okay, we're holding that for just a second. I am going to, give me just a minute. I'm going to stop sharing my screen because I want to pause the recording and